Okay, morning. Welcome to this fifth section of this webinar in Spatial Data Science. Today we have Professor Mário Figueiredo that we will talk about something exciting, which is back to the basics. Denoising Poissonian images using optimal linear estimation. Mário, let's go. Stage is yours.
Thank you, Amilcar, for the introduction. I'm glad to be here. So I'll jump right in. So let me see. Can you see it in full screen or not?
No.
What about now?
Yeah.
It's full screen?
So, more or less. So we still see the toolbar with.
So why that? If I put it in full screen, sometimes it doesn't work. Let's see if it works.
It's okay.
But it's okay, right? So we see a menu with the home and tools. But
what about now?
Okay.
It's the same, but it's fine. I mean, we can advance.
I just moved to.
You can read everything.
We can see.
Yeah.
Isn't it full screen?
What do you mean by full screen?
Well, full window in your Zoom window.
No, not yet.
No?
But it's okay.
Okay.
Yeah.
Okay, we can see the presentation. Yeah.
Okay, no problem. So this is stupid. Okay, so the title of the presentation is Back to Basics, Denoising Poissonian Images using Optimal Linear Estimation. And this lecture could almost I'm sorry, it was this talk could also almost be like an exercise from a book in spatial statistics, but applied to images with a few tricks. Okay, and this is the final part of the PhD work of Milad Niknejad, which I co-supervised with my late colleague José Biocas Dias. This was done in 2019, 2020, published in 2020. So just to justify why I'm here at a Spatial Data Science seminar. So of course, as you probably know even better than me, Poisson processes are ubiquitous in spatial statistics. So this is just an example I stole from the web. This is an example of a Poisson process that describes the location of some trees, white oak trees, somewhere in Michigan. And so a Poisson process is a collection of events in this case it's spatial, in the spatial case in space. And there's an underlying intensity, which is the intensity that controls the occurrence of these events. And most of the times the goal is to you're given these black dots, so the events. This could be like trees, or it could be something else, and the goal is to try to estimate the underlying intensity of the process. I'll come to. So this has applications in many different areas. So in spatial statistics, in many different areas of spatial statistics, including astronomy, which is a sort of a form of spatial statistics. So this is an image, so a deep space image with in invisible light, and these are photons. So on the left you have photons. And on the right, you have an estimate of the intensity of the source that produces those photons. So this is very low count. So each white dot is a pixel. So this is an image. So the black pixels are just 0 photons, no photon arrived. The white pixels, they add 1 photon. And the goal is to kind of come up with this intensity. So this of course, there's more to this. I'm not going to talk about astronomical imaging. But again, the goal is the same. You have intensity estimation problem, which is you're given photons, and you want to estimate the underlying intensity of the process. So what do you mean by intensity? So if you're looking only at 1 pixel, the underlying intensity would be the value of the image on the right, whatever that means. And as I'm sure you all know, Poisson distribution has this expression. So you have intensity lambda, and the probability that you have k whatever in some spatial area during some time. So in this case, for an image, the spatial area what you're looking at is the 1 pixel, say one of the sensors in the imaging device, and the time is the integration time. So the time that the image during which the image was acquired. And so this intensity, in this case of an image, would be measured in photons per unit per time. So actually after multiplying by the area of the unit and by time. So this is the expression. This is the probability that you have k photons given the intensity, and it's given by this expression. And this is the curve. So these are classical. It's from Wikipedia, of course. And if you have so intensity is 1, you have a quite high probability that you observe only 0 or 1 photon, and then it decreases very quickly. If of course the lambda, the intensity could be less than 1. In this case, the most probable observation is 0 photons. And this is how it looks for lambda equals 4, for lambda equals 10. And it's clear that as lambda becomes large, the distribution becomes not very different from a Gaussian. It becomes more symmetrical, and the Poissonian nature becomes less relevant. So, but the main property of the Gaussian of the Poisson distribution is these two. So the expected value of the counts is precisely the intensity. So the intensity has the same unit as counts per unit, whatever, area and time. But the variance is also proportional to the intensity. And this is what makes it difficult to handle in terms of imaging, because you have the signal to noise ratio is proportional to the intensity of the image. So in an image, the area that is bright, it also has more variation. So noise, I don't like to call it noise because it's not exactly noise. And in areas where you have low intensity, you also have lower variance. So it's not like you can model it as additive noise. It's more complicated than that. So when we talk about Poisson imaging, the idea is that we're talking about imaging in a regime where the Poissonian nature of the photons is relevant. Okay, so this is an example of an image of the scene acquired under very different conditions. So the one on the top left, the average number of photons per pixel is of the order of 10 to minus 3. So most of the pixels, as you see, are black. So there are no photons. Only a few pixels have photons. And then this goes from 10 to minus 3, minus 2, minus 1, 10, 10 squared, 10 cubed, up all the way to 10 to the 5th photon. So for high intensity, high average number of photons per pixel, so for high intensities, you start seeing that there's almost no noise. Okay, so it becomes really clean. And moreover, that's even more important, the noise that you have is almost Gaussian. So you don't have to worry about the Poisson nature of the photons. So the Poisson nature of the photons only makes a difference, and it's only relevant in low count regimes. Right? It's sometimes called photon limited imaging. So when you have very dark situations, or in astronomical imaging, or in other applications where you have in microscopy. So this is an example from a focal microscopy, which is again a very low photon count regime. And this is just an illustration that is used to show that in this case, so it's clear that it's a low photon regime, because you can actually see the point nature of the observations. If you denoise it, what do we mean by denoising? Denoising is simply the operation of somehow estimating the intensity, the underlying intensity of each pixel that gave rise to this number of photons in each pixel. So in this image, I guess, I don't remember, but I think this is the average intensity is like 2 or 3. And so it's relevant that it's Poissonian. It's very different from Gaussian. And if you pretend that it's Gaussian and try to denoise it using Gaussian methods designed for Gaussian data, it doesn't work so well. It works actually much worse. For example, in high intensity regions, it underestimates the signal to noise ratio, and it doesn't do a good job. Okay, so let's look at this intensity estimation problem as an image denoising problem. And image denoising is arguably the oldest image processing problem. So it goes back to the 60s. It started being studied when the first astronomical satellites were sent to observe. It was actually the first work in image processing was probably done in the Jet Propulsion Lab in the US in the 60s. And it ever since, of course, today is a huge area, of course. And denoising is probably the simplest image processing problem. Okay, so in image processing, in image denoising, you typically have a noisy image Y, which is obtained from X, which is the underlying clean image, by adding noise. So I'm putting this adding quote unquote because it's not always added. So if your image Y is Poissonian, X is the intensity, and it's not addition of noise. It's just that thing that you observe is a Poisson process that has X as the intensity at each pixel. So it's not addition. It's just addition in a sort of in abstract sense. Okay. So there's so much work in image denoising that, and the state of the art is so high in general, especially for Gaussian noise, that in 2010, Feynman, Mühlenfahrt, and Chatterjee wrote a paper whose title was "Is Denoising Dead?" So is it a solved problem? Well, the answer no, it's not. And if we look at how many papers are being published today in denoising, and one good way of knowing if a paper is working on denoising is that if they cite what is probably the seminal, so this seminal paper of one of the methods for denoising, which is very well known, which is called BM3D. So everyone that does denoising needs to compare with BM3D. And so by checking how many papers are citing BM3D, we have an idea how many papers are being published every year on image denoising. And it's around 2,000, either around 1,000. So that's definitely not a dead area. Okay, until recently, most state-of-the-art methods for denoising, so or if you want for intensity estimation in Poissonian images, were patch-based. And I'll explain in a second what a patch-based method is. Of course, nowadays we have deep neural networks, deep CNNs, if different flavors with different techniques, and I will touch upon that in a bit slightly at the end. Okay, so what is patch-based denoising? So patch-based denoising is sort of a, if you can look at it as an instantiation of this famous principle. I think it comes from back to Julius Caesar: divide to conquer. So the idea is very simple. You have an image, you decompose it into patches. Okay, a little patch, say 8 by 8. You denoise that patch somehow. It doesn't really matter how for now. And then you put it back where it was, denoised, and you do it by considering all possible patches. And of course, you will consider overlapping patches. And if you denoise two patches that overlap, when you put them back where they were, you average the pixel estimates that you obtain. So graphically, it's something like this. So you want to say denoise this patch. Here, you look for, one of the ways of doing it is you look for patches in the image that are similar in some way. So if you look at these patches, they all look sort of similar. And then you collaboratively use them to produce an estimate of the patch that you're interested in, this one, which uses the others as an auxiliary to denoise this one. So it could be many different things that can be done here. And then once it's denoised, you put it back where it was, and you do it for all possible patches in the image. And this is how you run a patch-based denoising. Okay, I won't go into the details of these, but there are many, many ways to denoise patches. This is the one that kind of implicit in this picture is that you exploit patch similarity. So in this case, you would look, when you want to denoise a patch, you look for patches that are similar enough, and then you say average them, or do something a bit clever than that. You can do sparse coding, you can do different types of minimum mean squared error estimation using some priors. You can do many different things. And you can do it as a huge variety of methods. You can do it non-parametrically. You can do it semi-parametrically. You can do parametrically. You can do many things. Okay, it's not very important because this is when I'm talking to, say, denoising experts. They like to see their names there. Okay, so what do we mean by Poissonian images? So as I was telling before, so Poissonian image is an image. So each of these now, these Y and X now are now images, or a patch of an image, or a full image. It doesn't really matter. And what this says is that each of the components of Y is a Poisson variable with the intensity given by the corresponding pixel of the underlying intensity image. Let's call it clean image. Okay. And since they're all independent, this is a product of all these Poisson distributions. And of course, the goal is to your given Y, a noisy image, and you want to estimate X, the underlying intensity process. Well, like I said before, the key feature of Poisson distributions is that the variance is equal to the mean. Okay, this is something that will be the key to what we will do. So there are many ways to denoise Poisson images, denoising quote unquote, because it's not exactly denoising, because there is no such thing as the clean image. It's just the observation process that follows a Poisson distribution, and you want to estimate the underlying intensity. So one of the classical ways is to break this equality between variance and mean using some nonlinear transformation. And this is very famous. It's called Anscombe transformation. There's some nonlinear transformation which you apply to y that makes the variance approximately constant. And if the variance is approximately constant, then you can use a method that is designed for Gaussian noise, for additive Gaussian noise, because in that case you have the noise variance is constant. This works reasonably well, and it's at the basis of most of the state of the art up to the mid 2010s, which is just do the variance stabilization transformation and then apply some state of the art method that is designed for Gaussian noise, which is most of them are. So there are other methods. So there are Poisson non-local means, so patch-based methods that take into account that the images are Poisson. When you look for these similar patches, you have to take into account that they are Poisson distributed. So the way you compute similarity needs to be done with care. And there are other methods. And of course, there are deep convolutional neural networks, which I will come back to in a second. Okay, so here is a slide that gives title to the talk. So back to basics. What would you do? So this could be an exercise in a estimation, that spatial statistics book or linear estimation, first introductory course on linear estimation. So this is a classical problem in linear estimation. So you have a vector x and a vector y. They are somehow related. We'll come back to that. And the goal is to estimate x given y. So you're given y, and you want to produce an estimate of x. And you want this estimate to have this particular form, okay? It has to be some matrix multiplied by y plus some vector, okay? So they don't have to have the same dimension, so it could be n and m. In that case, of course, matrix B needs to have the adequate dimensions, and of course, A has the same dimension as x, okay? So the classical criterion to do this is look for B and A that minimize the expected value of the squared error. So the minimum, so it's linear minimum mean squared error, LMNC. So you want to find A and B. So you want to minimize with respect to, say, B prime, A prime, the expected value of the difference between the true x and your estimate x hat, which is given by by plus A. Okay. And this can be done in closed form. It's classical. This is probably the second exercise in a book on linear estimation. And you know that you achieve this optimum by choosing B to be given by the following. So this product of these two matrices. So sigma YY is the covariance of Y. Sigma XY is the cross covariance between X and Y. Mu X and mu Y are the expected values of Y and X. Okay, this is easy to understand. For example, notice that if sigma XY is 0, so if there is no correlation between X and Y, this covariance will be 0. So this guy will be 0, B will be 0, and this guy will be 0, and A will only be mu X. So which means that if you're estimating X from Y, but X and Y are uncorrelated, your best estimate is just the expected value of X. That's it. You gain nothing by looking at Y. But if there is some correlation between B and between X and Y, then there is this B is not 0, and you're using information from Y to produce an estimate of X. Okay, so what are the consequences of doing this in the Poisson case? So it's very easy to compute all these objects. Okay, so the expected value of Y equals the expected value of X. They're all the same because the expected value of Poisson is exactly equal to the intensity. So the expected value of the intensity is mu X. So the covariance between X and Y, this is again very simple to do this computation. It's like half a line. So it's exactly as if this was zero mean Gaussian noise. So the covariance between X and Y is exactly the same as the autocovariance of X. And now this is one which is different, which is if this was additive Gaussian noise, the covariance of Y would be the covariance of X plus a diagonal matrix with the variances of X. But since X is Poisson, but since Y is Poissonian, the covariance of X is the same as the mean of X. The covariance of Y is the same as the mean of Y. And this is what makes these easier to do. So the covariance of y has this simple form, it's covariance of x plus a diagonal matrix with the means of x. However, so now once you plug these, just plug these quantities in the previous slide and you get this. It doesn't really matter. The details, just something that you can compute. However, this is easier said than done because, of course, you don't know the mean of x, and of course, you don't know the covariance of x because you don't know x. You want to estimate x. So, how do you go about doing this? So this is where a trick, which is sometimes called the pilots, is used in this case. So let me. So after last time I gave this talk, second time actually, I think. This famous guy, Payman Milenfar, tweeted about this pilot estimate. So this is an old technique. It was just explaining it, and so I think this is a clear explanation that explains what this notion of pilot estimate is. So he's wearing a pilot shades. That's not why it's called a pilot estimate. So suppose that you want to do some processing. Okay, you want to estimate something that depends on y. And you know that the estimator is linear. Just forget about the additive term. You know that the estimator is linear, but it's linear with a matrix that itself also depends on one. Okay, so it's not linear. Okay, it kind of looks like linear, but the matrix depends on the observations themselves. Okay? This is very common in machine learning. It's kind of similar to what transformers do in a sense, with some nonlinearities in the middle. So how do you do this? Okay. So it's very often you do this using a pilot estimate. What is a pilot estimate? So first, you take y, you do some sort of more basic denoising. You denoise it using some auxiliary method, okay? And so you do something called a pre-filter. And then you use this pre-filtered image to compute w. And then now you apply w to y, okay? So you do the pre-processing of your data before you compute w, okay? And by using this w of z instead of w of y, the raw, you stabilize the effect of the noise on this matrix. Okay, so this is exactly what we're going to do. So to compute mu and sigma, we're going to compute a pilot image using some auxiliary denoiser, and then we take that denoised image, and from that denoised image, we estimate mu x and sigma x, and then we apply our formula. Okay, so this is how it works. You take some Poisson denoiser. Take your favorite state-of-the-art method, BM3D, for example, after variance stabilization. You compute a pilot estimate. So you apply this denoiser. It could be BM3D type, it could be something else. Okay, you compute a pilot estimate. Then once you have a pilot denoised image, okay, for each patch, you take patches of the image, and for each patch, you look for similar patches using some criterion. It could be Euclidean distance or something, okay? Doesn't really matter. And you build a collection of patches around some window of each patch. Okay, now from this window of patches which are denoised, you estimate mu and sigma, okay, from this collection of patches. And now you plug them into the formula that are the linear minimum mean squared error, and you just denoise those patches using the formula. Okay, that's it. It works like this. Then you return the patch to the location, you average overlapping estimate. So the trick is use the linear minimum mean squared error to denoise the noisy Poisson noisy patches. The linear minimum mean squared error requires knowledge of the mean and the covariance. How do you get them? You build a pilot estimate from another denoiser, and you estimate it from that pilot denoised image. Okay. You maybe repeat this twice or 3 times, because now you have a denoised image, and you can think of that denoised image as a better pilot. Now you take your denoised image, you re-estimate mu and sigma, and you repeat the procedure. Okay, and it's usually you do it like twice, 3 times, no more than that. Okay, so let me show you some examples. So what base denoisers have we used? We used what state of the art at the time, apart from deep networks, which is this non-local PCA and 2 versions of the variance stabilization plus BM3D. So variance stabilization is that method that you start by doing some nonlinear processing on the Poisson image to make the variance constant, approximately constant, and then you apply a method designed for Gaussian noise. Okay. So the signal to noise ratio is controlled by scaling the peak value of the original image. So for example, if the peak value of the image is 2, it means that the pixel with the highest intensity is 2, which means that the highest expected value of number of photons per pixel is 2. Okay, if it's 5, then it's 5, and so on. Okay, we repeat that main loop twice, as I said. The patches are 8 by 8. The search window for similar patches is 40 by 40. And the number of nearest neighbors is 30. So we find the k nearest patches inside a window of size 40 by 40, of patches of size 8 by 8, to estimate the mean and the covariance of each for denoising each group of patches. And here are the results. I'll show you images in a second. So the idea is this. So this is for peak 2, peak 5, and peak 10. So peak 2 is a quite noisy image. It's very low counts. And this is the VST, so variance stabilization, plus VM3D. And this is a signal to noise ratio. And what we see is that you take the image produced by the signal to noise ratio produced by the original method, you apply the LMMSE filter, and you improve the SNR by around something from 0.3 to 0.8 to 0.6, around this quantity, so around half a dB. And it's always like that. It's always sort of half a dB better. So half a dB may not look a lot, but it's quite visible, okay? Especially in Poissonian images. So this is an example for peak 5. So this is the average number of photons per pixel in this image is 5. Actually, the brightest pixels in this image have an average of 5 photons. So this is what you obtain using this method, and this is how you improve it by post-processing with the LMMSE filter. In this case, you improve by 0.4 dBs, but you can see that the image is much nicer, especially in flat regions. So this is the same, but for a slightly better method. So it's the second version of this variance stabilization plus VM3D. For example, for the cameraman at peak 2, this guy gets 22.04, and this guy gets 22.34. So this is already like 0.3 dBs better than the previous one. But our LMMSE post-processor keeps on doing its job, which is takes this and improves it by around 0.2, 0.3, around 0.3, in this case 0.4 dBs. Okay, again, an example. So this is for peak 10, so VST plus BM3D, in this case, the second version. This is 26.5, this is 27.3. So in this case, it's 0.8 dB improvement, and it's much nicer looking image. So this is kind of the results. We have, of course, more results. I won't bore you with a lot of results. So this is seen as a post-processing. So you have a pilot estimate, a pilot denoised image using any denoiser that you want. And on top of that, you can always squeeze a few more tenths of the dB using this LMMSE estimate, which is very cheap. This costs like a few seconds of processing. It's very, very cheap. There are very fast and efficient ways to do this batch processing because it's been around for quite a while. What about deep neural networks? Okay, the table on top is the table from the previous slide. It's the same table. So in 2018, this is at the time when we did this, it was the best deep neural network-based method for Poisson denoising. It didn't get much better, maybe 0.1, 0.2 dBs. Okay, so this is the result. So that we didn't have access to the architecture at the time, and I haven't tried again. So they compared their methods with the same method with which we compared ours, so which is variance stabilization plus BM3D. Okay. And what they show is that their method gains, on average, with respect to to variance stabilization and BM3D, something that goes from 0.1 dB, which is we gain 0.2 here, to around 0.3 dBs, which is essentially what we gain. Actually, sometimes a little more. Okay, so what this shows is that our post-processing method, which is very cheap computationally, achieves results which are basically on par with a deep neural network that has 20 layers, that was trained on 10 million patches, and it took quite a few days to train. And our method is very simple. This is like one page of, 10 lines of code on top of any denoiser. And it achieves the same type of results that you achieve with a deep neural network that requires a huge amount of training. And here there's no training involved. So this works for any image. All the information that you need is contained in the denoised image itself. You don't need any training data. You don't need anything. You just need to exploit very carefully the fact that the image is Poissonian, and so you can compute the linear mean squared error in closed form if you're given a pilot estimate of the image. Okay, so that's it. So my only final remark is that it's very pleasing when you find a problem where you can use a very basic and tool that you can find in introductory books and still use it to obtain state-of-the-art results in some problem. Of course, you have to use it in a clever way. Thank you for your attention.
Thank you, Mario. Quite interesting presentation, quite interesting topic. Time for some questions. Who want to open this? I will. Mario, something. Well, this is not my backyard, but let me ask you one thing. So your point is you do local estimators, linear estimators, by using some auxiliary patches in order to estimate the covariance, X covariances, and the mean and the mean of X. These days. First, you have to choose similar patches.
Right.
Those covariances between X covariance is a kind of average of those patches, or you choose the most common, or how do you choose?
No, it's average. It's average. Just when you have a collection of patches which are similar,
yes,
you assume that it's important to have similar because you want to assume that they are sort of in a region where the intensity is homogeneous. Okay, so you're looking for a region, even if not spatially contiguous, it doesn't matter. You want patches that have sort of the same intensity. Okay, and then you use the patches, you vectorize them, and then you just compute the sample covariance. That's all.
Ah, yeah, you put all together. Okay.
Yeah.
Okay. Good.
And the sample mean and sample covariance, just standard formulas.
Okay. So and you apply to that patch. Any other question? What about when you try the next patch to do the next estimator, local estimator?
Yeah.
What happened to? Maybe I'm doing some confusion. What is the artifacts in the boundary? There's
no, because you choose overlapping patches. So you overlap each pixel.
Okay.
Each pixel is denoised several times because it belongs to different patches, and then you average the estimates.
Ah, okay. So there's no artifact.
There's no artifacts. Okay. If you did it like that, if you did it like with if you had non-overlapping patches, of course it will be very blocky. It would be awful.
Yeah. Sure,
but you keep overlap. But sometimes you don't do full overlap. So if you have 8x8 patches, you can move like 2 pixels by 2 pixels instead of 1 by 1 to make it a bit faster. But if you have 8x8, you don't move 8. You move like 2 or 4. So you need to guarantee that there is some overlap, so that there are no artifacts.
Good. Perfect. So your conclusion is that simple is the best.
Not all.
Sometimes. Not always.
But it's great fun when you can use something very basic and make it work very well.
Good. Any other question? So simple that those guys.
So these things like how the patches overlap, how much they overlap, the actual structure. So this influences the results.
Yes, a bit. If you overlap more, the results are a bit better because you get an extra denoising effect by the fact that you're averaging the overlapping patches.
Well, that and the number of similar patches that you consider, right? So there's a lot of things to tune here. So I'll set
size of patches, search window, and number of. But we in the papers we have studied all that. So the number of similar patches that you use to compute the covariance, it improves as you go up to 30 or 40, but then beyond that you don't gain anything because it start being difficult to get that many patches which are really similar. The search window it just becomes more expensive if you have a bigger search window, and you don't gain much because you would just be able to find a few more similar patches if you enlarge the search window. But the patch size, that's important. Okay, if you and there's other tricks that make these work well. Typically, what we do is for each patch you apply a statistical test to see if it's flat. And if it's flat enough, you don't process it. You just replace it by the mean, okay, which is much faster, and it actually gains like 0.1 dB or something just by doing that trick. Especially in very low photon count situations, which are very noisy. Sometimes the best estimate for the patch is just flat.
Interesting. Any other question? Just a curiosity, Mário. Back in the 90s, this kind of problem, not for denoising, because you want to get exactly the structure of this Poissonian distribution, but linked to diamond. Exactly, diamond mineral concentration, because the best way to estimate this is to assume the Poissonian distribution of this. It's so random. Okay, folks. If let me see, no hands. Time to thank again Mário for this very interesting and presentation. Mário, thank you so much.
Okay.
Have a nice day.
Thank you. Thank you all for coming. Have a nice lunch.
Okay. See you tomorrow. Okay. Bye bye.